So, to explain to us about the construction of lithium batteries and which components are essential in terms of fire and explosion risks, we are very pleased to have with us Professor Johannes Landesfeind from the University of Agder. Landesfeind has broad experience in battery research, and at the University of Agder, he combines his experience from academia and industry with his network and colleagues to create competencies in battery education, development, and research. So please welcome to Professor Landesfeind. The stage is yours.
Perfect. Thanks a lot for the introduction. I hope you can hear and see me because I don't see anything, so I hope that works. But maybe can somebody confirm that you're seeing the screen?
Yes.
Perfect. Great. Thank you so much. So I have 20 minutes ish to give you a brief introduction, and I discussed that beforehand for you and the plan that you have today in your meeting to understand the essentials of what makes batteries, lithium-ion batteries, especially potentially dangerous, and where exactly that comes from everything inside the battery. And I want to start in very brief, just to put this all into perspective, into battery technology as a broad. Right? This is not something that is very new. First batteries were developed in the 1800s by Alessandro Volta, and the principle of how a battery works since then is not so much different, other than the materials used. In the end, even these very first batteries, how you may also know it from household batteries, is made of two poles, a positive and a negative pole, which in this very first batteries was simply made out of copper discs, zinc discs, and they are separated, and we will get back to this when we're also discussing lithium-ion batteries. They're separated by, in this case, a cloth that contains ions. And this very same principle is also what is used in lithium-ion batteries. Since these very early developments of batteries in the 1800s, there were very many different battery types that were developed, and they're working to a large extent very, very well. And to put this into perspective a little bit, this is one example. In the, maybe I just show the entire slide. In the around 1900s, a large fraction of all cars driving around worldwide were electric vehicles. You can see that on the bottom right corner. It was pretty much 40% electric vehicles. More than 100 years back, 40% steam, 20% combustion. And that then took over once then Henry Ford started with mass producing the Model T. And to demonstrate even back then, right, these electric vehicles were driven by lead acid batteries, similar type of batteries that you have in combustion cars nowadays to start up the engine. So this lead acid battery chemistry, battery setup, it's been developed for over 100 years. It worked like a charm, even 100 years back, and was able to drive cars for hundreds of kilometers without a problem. It was a 100-mile driving range, 160 kilometers, even more than 100 years back. So to link this to, if that was working already 100 years back, so nice, why are we not all driving around with lead acid batteries today? I want to show the following graph as the motivation for why we're discussing specifically lithium-ion batteries. This graph shows the energy density in watt hours as the unit of energy, either per mass on the y-axis or per volume on the x-axis here, for different types of battery chemistries. You can see the tiny blob here at the bottom. This is how much energy per volume or per mass one can store in this lead acid chemistry. In the nickel cadmium batteries that were forbidden some decades back, or the nickel metal hydride batteries, which is the chemistry that you get nowadays if you're buying rechargeable batteries, AA or AAA format for your household. This is that type of energy density. And the reason why electric vehicles nowadays, home storage units, your smartphone, your smartwatch are using lithium-ion batteries is that the lithium-ion battery energy density is significantly higher than any of the other chemistries in that sketch. And this is basically due to one key reason, because all these battery chemistries here in the bottom left are functioning with water. And this is one key change, which is also safety relevant. We'll get back to that in a second. And a lithium-ion battery does not contain any water, but it uses another medium to transport ions, and that is non-aqueous, meaning basically just non-water solvent molecules, similar to, for example, ethanol or isopropanol, which have the downside of being flammable, but allows, on the other hand, this higher energy density. So what I want to go through in the next couple of slides is to explain the components of such lithium-ion batteries, what they are made of, and then link this after to the safety properties of lithium-ion batteries. So in a nutshell, a lithium-ion battery works very similar to these first Volta batteries 200 years back. One has in the end a positive pole, one has a negative pole, and in an outer electric circuit, electrons are being transported, and this is what is doing the actual work, driving your car, operating your smartphone processors. And this external current in a lithium-ion battery has to be balanced inside with the transport of positive charges. And this is the lithium ions, which is sketched here as these green dots, which are basically during charge and discharge moving between the positive and the negative electrode back and forth. And those lithium ions, and this is also one of the key points to take away for you for this workshop today, is the lithium ions are stored in the crystal structure of the materials that are used on the positive and the negative side. And in this operation during charge and discharge, as I said, the lithium ions are traveling back and forth, and this is why very often this battery is also called a rocking chair battery, because it's like the rocking chair, the lithium ions being transported back and forth. And the way the lithium ions are transported now is essentially a key difference to these aqueous batteries like the lead acid battery. The lithium ion is transported in this non-aqueous electrolyte, which is now sketched here as this orange solvent molecule. This is the key difference, lithium-ion battery versus all other batteries. This is not water, but it's something else. And in this process, typical materials, this is also safety relevant, as we will see in a second, so I'm briefly touching that. Typical materials that are used on the anode side is graphite. It's very similar from the chemical composition, is pretty much the same as if you're doing a barbecue, having coal. It's carbon, it has a different structure of the atoms, but it, in a way, as it's also resembled in a picture, looks sort of like a shelf, and in these layers of the shelf, the lithium ions fit in. On the cathode or the positive electrode side, this is typically metal oxides that are used here, and this is safety relevant, and I will show this briefly and motivate that on the next slide. So generally, maybe going back, the safety relevant topics of a battery is mostly the electrolyte itself and the cathode material, this positive material. So these positive materials for the positive pole in a battery, in a lithium-ion battery, sorry, they can have 3 different types of crystal structures. And this is sketched here in 1D, 2D, 3D structures, and I briefly want to show this a little bit more visual. So this is LFP, remember that name, it will come back in a second. An LFP chemistry for a lithium-ion battery. And if I slowly move around the orientation of this crystal structure, I hope that works in the streaming. Sorry if not, but you should be able to see this is sort of the lithium ions being this purple dots are in this crystal in sort of a channel, one-dimensional channel. And because of this crystal structure, this material, as we will see in a second, is safer than other materials that are used in lithium-ion batteries. For example, this material here. This is a lithium cobalt oxide. And the key difference, as you can see here, if I'm moving around the crystal a little bit, the lithium now is in layers. It's an entire layer, which is basically only lithium, these purple dots. And if one takes out, you can imagine this being a bookshelf and the lithium ions being books, and rather than the shelf being bolted to the wall, it's one layer of the bookshelf just resting on the books. So if you take out all the books, the bookshelf will just collapse. And it's exactly the same thing that happens here. If one takes out too much lithium of these types of layered materials, then the structure will collapse, and that has safety implications. So key takeaway, there's different types of materials to use for the positive electrode sides, and they have different implications when it comes to battery safety. But what is important, and also in relation to aqueous batteries, like your household batteries, if you're buying a rechargeable household battery, this AA format, it's pretty much always a nickel metal hydride battery, and all the chemicals inside is pretty much always the same. In a lithium-ion battery, what makes this also a little bit of a challenge, there's not one type of lithium-ion battery. One combines materials from the negative electrode with materials that work as a positive electrode. But for both these electrodes, there is a portfolio of materials that one can choose from. And then one has a large amount of combinations that for specific applications then have upsides or downsides. But it's not one lithium-ion battery chemistry, but it is a portfolio of combinations, making then also the safety very different for different type of combinations. But these materials that are storing in the end the lithium ion for the positive and the negative electrode, these are what is inside all your batteries, the lithium ion batteries that you have in your laptop, your smartphone, or whatsoever. And the way these materials are assembled into a battery is briefly sketched here on the next slide. This is the materials for the negative side, which is called the anode, and for the cathode, which is the positive side. These materials are made into a paste. So one adds to this powder, looks like ash in both cases, it's like a black powder. One makes a paste out of it. You can imagine it being like baking, making a dough, a very liquid dough, like waffle dough, for example. And then this is spread very thin on metal foil. And this makes the positive and the negative electrode in a battery. And to make this battery work, then the metal foil is in the end connected to the plus and the minus, the outside poles of the battery. And to make these two electrodes work, they need to be sandwiched together. But it's very important that, of course, inside the battery, they're not touching each other, because then it would just be an electric short circuit. So what is added between these two electrodes is what is called a separator. If you remember this Volta battery in the very beginning, there it was a sort of a cloth which contains acids or bases and contains ions in the end. So in the case of lithium-ion batteries, this is typically looks like a very boring plastic film, which is super thin, and it is porous. And this porous film is then soaked with this electrolyte, which contains the lithium ions and contains this solvent, which now is not water. And this allows then the ions to travel between the two electrodes through the pores of the separator from the one electrode to the other electrode. And just to put this a little into perspective, right, why it's not so straightforward to make good batteries, all these layers that you also seen on the slide before is all super, super thin. So an example here for this separator plastic film that is used is sketched here on the bottom. This is 25 micrometers thick, which is hard to put into perspective, but the brown dot here, this is the size of a human hair. So it's all layers that are super, super thin only, and then need to be manufactured with a high quality so that there's no particles sticking out and possibly puncturing such a separator. And then this is what it would look from the side if you were to open your smartphone battery and cut it in half. Please don't do that, but if you were to do, then this is what it would look inside. You would see this copper foil here, which is this copper anode as it's sketched here. Then there's graphite particles on the positive electrode. You have this thin separator layer that avoids that there's a short circuit, and then you have the particles on the positive electrode side on top of a current collector, which is connected to the outside. All of these super thin layers, and this is how basically all lithium-ion batteries are set up, is different sorts of materials for positive and negative, but in the end it always has this layered structure and this, if I go back, in sort of coated on these metal sheets. And this is the same setup in your smartphone, in your car. The only thing that differs then is how these sheets are basically assembled and stuffed into the battery. And there's 3 key formats for that. It is, for example, a pouch cell, which you have in your smartphone, for example, or these newer laptops or tablets, where these layers are basically stacked on top of each other, and then they're sealed inside a bag, which is pretty much the same bag type that you have in coffee beans. It's an aluminum bag which has a thin plastic coating. And this sort of battery format allows to pack a lot of material into a small volume. But of course, as you may know from the coffee beans, right, it's not very rigid, this housing. So it's very easy to puncture through if, for example, there was an accident in a car. So typically that is also why then in cars, one doesn't use these pouch cells, but one uses these cylindrical or prismatic hard case cells, where these layers in the cylindrical cell format is the same material altogether. It can be the same material altogether, but in the cylindrical cell, they are wound up like a spiral and then put into a solid metal can. So that allows to have more stability mechanically. And similarly in this prismatic hard case cell, which is basically the same as the pouch polymer battery, but in a rigid metal housing. So for all these different cell setups, however, the safety properties, the mechanical properties are, of course, different. But what going over to the safety aspect of lithium-ion batteries, what is a challenge is that if, for whatever reason, we will get to that in a second, a lithium-ion battery catches fire, it is a very vigorous reaction, and that is very different to aqueous-based batteries. And I want to show an example here. I hope this works. So I hope it's not too loud on your side. You should be able to hear sound. What you're going to see here now is a demonstration of a lithium-ion battery fire. And what is the batteries that are put on purpose here on fire corresponds, just to put this a little bit into perspective, if you know these electric scooters to drive around where you can stand on, if you put 2 of these scooters next to each other and you were to set those batteries on fire, this is a similar scenario here in terms of the energy content that is burning. So I'll play this. I hope this works out fine. the point, I can stop this briefly. I hope that was working fine, but other than really a fireball blowing, it's not so much one can actually see. But what is important to mention here on the right-hand side from this video, this is a standard fire extinguisher that is trying to extinguish this battery fire. And the battery fire is not very impressed by that. And what I want to use the last couple of minutes for is to explain why this is and how in the first place this could happen. So generally, in the interest of time, I don't have all the different methods to make lithium-ion batteries safe. There's many different components that avoid that lithium-ion batteries are intrinsically unsafe. They are properly tested. In comparison to a combustion cars, they are much safer. But in a car, of course, there can always be something happening, being a mechanical deformation. You have a crash, for example. If for whatever reason a battery, say in your smartphone or the laptop, is misused on purpose or by faulty programming, and the battery is overcharged or over discharged, all of these methods could lead to an internal short circuit of a battery. If you're misusing the battery, then you might also, for example, if you have a battery pack for a power tool and you just throw it in your box with all other metal tools, it might short circuit the poles. If you're heating the battery, for example, you leave your smartphone in Texas under the windshield. All of this kind of planned or unplanned misuses in the end lead to local overheating. And this local overheating may lead to this thermal runaway reaction that you saw on the video before. And the key difference in a lithium-ion battery fire versus a standard fire is sketched here in brief. So for a standard fire, there's 3 key requirements. It's oxygen, one needs fuel, and one needs heat. And then one can make a fire. Then the standard fire extinguishers typically work in a way that they remove the oxygen source and then the fire stops. And this same triangle is also relevant for lithium-ion batteries. One needs oxygen, a fuel, and heat. Heat may come from either of these misuses or an accident, as I sketched on the slide before. The fuel in a lithium-ion battery is actually the electrolyte, which is now not water. So it is a solvent that can burn in the end. But that is not the key challenge. The key challenge in lithium-ion batteries, what makes it so dangerous, is the oxygen does not come from the environment. But if you remember this one type of crystals for the cathode, which has this bookshelf structure, if this material becomes too hot, or if one takes out too much lithium, then these layers collapse. And in collapsing of these layers, there is oxygen being evolved. The crystal basically decomposes and gives away oxygen. And this is the key challenge to take away maybe for your workshop today, that in a lithium-ion battery, all the oxygen component and the fuel component is already inside the battery. And that is also why the best way to extinguish a lithium-ion battery is to remove the heat. Because all the other components are already inside, you cannot do anything about it. That is why a standard fire extinguisher does not help so much. So in very brief, an example, if a lithium-ion battery becomes too hot, best thing is to cool it down. And I'm pretty sure the colleagues from the fire department will have some more insights on that. This is an extreme example of just immersing the entire battery car into a water tank to cool it down. And the 2 points, if I may, I want to mention last is there is a difference in different types of these materials. This is sketched roughly here, but without going too much into detail, these LFP materials, which has this one-dimensional channels, there the crystal structure is more stable. So even if it is heated up, it does not give away oxygen. That is why these materials are typically safer. And the standard material that, however, is used in cars is one of these layered materials that decomposes at 200 degrees Celsius-ish. a little bit depending on the material, and gives away this oxygen. And the reason why one uses this material, not the 1D material, is that you want to drive with your car as much as possible, and the 1D material typically only has half the driving range, ballpark. So if there ever was a lithium-ion battery on fire, then the gases that are coming out is a mixture of carbon dioxide, carbon monoxide, and hydrogen. But the last point to make, what is maybe key, if one has an open exploded battery of some sort, then the dangers of such an open battery is the carcinogenity of the materials. These layered materials typically contain cobalt, which is reproductive, toxic, may cause cancer. The electrolyte, as I mentioned, is flammable. And in batteries, there's typically superfine carbon particles, which are fine enough that you can inhale them into the smallest pores of your lungs, and are also suspected to cause cancer. So whenever something happens there, ideally one contains all these materials as much as possible. And with that, in the interest of time, I would like to thank you so much for your attention. If there's any questions, I think that was not planned for this. If you have any questions, feel free to reach out to me, send me an email. I'm happy to answer and do my best.
Thank you so much, Professor Johannes Landesfeind. Now we better understand why and how a lithium battery acts during a fire, which is essential to figure out how to extinguish a fire within an electrical battery and make it easier for us to understand the remaining presentations. Thank you.
You're welcome. Have a good day.